Okay, so first speaker this afternoon is Marco Sarich, who's going to talk about projecting multiscale processes and clustering.
Yeah, thank you very much. Thanks for inviting me to Cambridge. My talk will be very much connected to Eric's and Jin Feng's talk from yesterday. So I will also talk about different coarse graining techniques and analyze them by looking at them as projections of the underlying transfer operator of the system. So maybe first the setup. So I want to analyze time-continuous Markov processes, this x of t. So you can think of Markov jump processes, for example, if you have a discrete or finite state space, or a diffusion in a potential. I assume that we have a generator. So for example, I will also assume that we have reversible dynamics, and we have a unique invariant measure or stationary distribution, which I will call mu. So this is this mu here actually. So then I assume, we have a generator, which means nothing else than if we initially distribute our process according to some initial density. So it's a stochastic density with respect to this measure mu, and we let the process evolve, and we see how the density changes under the dynamics. Then we know that actually these densities evolve according to this differential equation involving the generator of the process. So for example, if you have a Markov jump process, this generator is nothing else than a rate matrix, and you also call this the master equation. If you have a diffusion and a potential, then this L can be written as a differential operator, and you have a PDE here.
I am confused by mu zero is zero.
Sorry?
X? What is the function?
V0?
Yeah.
It's an arbitrary initial distribution of my process. I have an ensemble in the beginning at time 0, and I want to initially distribute it. It's a probability density. And it's a density with respect to this measure mu, so the stationary distribution.
So mu is a geometrical measure.
Mu is the invariant measure of my process. Of this process, of the diffusion. For example, the Boltzmann distribution.
The zero-time distribution, V0 x.
The V0, yes.
X?
Yes.
Initial distribution.
Yes, initial distribution.
So V equals 1 is your equilibrium distribution.
Yeah.
Yes. Yes, exactly. With respect to the mu. Sure. Yes.
Huh.
Okay, and then at least formally I can write this also, the solution in this form. So where I introduce actually here this more or less the solution operator of the differential equation, which means if I have some initial condition, the operator t of t just gives me back exactly the density at time t, so how my system evolved in time. And this object is called the transfer operator, because it governs actually the evolution of my densities under the stochastic dynamics. So this is the transfer operator. We'll see also another formula for this object. So now, as I said, I assume two things, at least for the first part of the talk, that I have this invariant measure, so stationary distribution for my process, and also that my Markov process is reversible. So for example, diffusion in a potential, because this makes a lot of the analysis much easier. We have discussed this already yesterday during the talks, because both of these operators are then self-adjoint in the appropriate Hilbert space. So first of all, I want to say, why am I interested in these objects? Because many of the properties of the systems, of the stochastic systems, are encoded in the operator. So if I can analyze the operator appropriately, I can understand a lot of my system actually. So for example, that's one example. If you have such a simple double well potential, imagine just a diffusion in this potential, I can look, for example, at the eigenvalues of this transfer operator. That's, for example, here for a certain amount of noise. And from the eigenvalues, I can learn something about metastability in the system. For example, here I have two eigenvalues which are very close to 1. Then I have a gap, and the others are not so close to 1 anymore. So I see I have two eigenvalues which are close to 1, which tells me that I will have 2 metastable sets in my system. So I can partition my state space into 2 sets, which will be metastable. And not only this, if I can also compute somehow the eigenvectors of this transfer operator, this is the blue curve here, then I can also learn about the position of these sets. Because I just have to see that I can approximate this eigenvector well by step functions on the metastable sets. So I know that the number of eigenvalues of the eigenvalue which are close to 1 corresponds to the number of metastable sets that are there. And if I look at the corresponding eigenvectors, the eigenvectors will be almost constant on the metastable sets. So this is actually also used for several partitioning algorithms, spectral clustering algorithms, that take more or less this transfer operator, look at the eigenvalues, look at the eigenvectors, and from this they try to construct a metastable partitioning. But there's more. For example, if I'm interested in something like hitting times of the process. So imagine this slide is our state space. Now I pick a certain set D in my state space, and I ask the question, what if I start at a certain point X? How long does it typically take? So what is the expectation value of the time until I hit this set? So how long does it take on average? Of course, I could do this by simulation. I could start at this X and simulate a lot of trajectories and just always measure how long did it take and build the average. But you can also compute these hitting times actually as a function of the whole state space by solving a linear system with boundary conditions involving, again, the transfer operator. So again, this object. So without simulation, you could learn a lot of about your stochastic system. For example, about metastability by looking at eigenvalues and eigenvectors, or by solving these linear systems with boundary conditions, you could compute other stochastic quantities like expected hitting times or something like that. Now, a problem with this approach in practice is, of course, that this transfer operator is an operator on function space, namely on this L2 space, weighted L2 space with the invariant measure mu. And also, of course, we have some state space, where our stochastic process lives in, this the r to the power d. So in order to practically solve these systems, we'll have to find approximations of this transfer operator. In the end, some finite dimensional approximations. But I want to discuss actually 2 options. So first of all, what we want to do is we want to find an operator t hat, which is in some sense almost t, so which approximates t. I will talk a bit more in detail about what I mean here. And there could be 2 scenarios. First thing is, the t hat is still an operator on function space, so it's not a finite dimensional space here. But the state space has a much smaller dimension. So we reduce here the dimensionality of the state space. This is then also referred to a dimension reduction. Or, and that will be also important for doing the numerics in the end, that the operator lives actually on a space D, which is even finite dimensional, because then what we want to do is we want to compute a matrix representation of it and really work, then we can really compute things. So this is then the part of the discretization. So of course, there are many choices how we can construct such approximations of the transfer operator. And I want to talk about a particular one, namely a projection of the transfer operator. This means I choose some subspace D, as just explained, could be still an infinite dimensional subspace where we reduce the dimension of the state space, or it's even a finite dimensional subspace. And then I just take the orthogonal projection onto this space D. And what I then do is I define my transfer, the approximating transfer operator t hat, to be just this operator here, which we call the projected transfer operator, which means I simply restrict my operator to the space D. And of course, if I let t act on functions of D, they don't have to be in the space D anymore. So what I do in the end is I do some best approximation afterwards to make sure that I'm in D again. So I take this particular approximation of the transfer operator. So now the question could be, why should I do this? Or is this a good approximation? Or in which sense can I analyze if this t hat is close to the operator t? And what I want to do is I want to compare the eigenvalues of these two operators. And particularly I'm interested in the dominant eigenvalues, so the eigenvalues which are close to 1, which describe the slowest process of the system. And there's a nice theorem about it, which actually tells me something about the eigenvalues of the original transfer operator and eigenvalues lambda hat of my approximating transfer operator. And it says the following. So if I have a self-adjoint operator, so here it's really important that we have a reversible dynamics, and we pick some eigenvalue of it. It can be one that is close to 1. It can also be some other eigenvalue. And I take an eigenvector which corresponds to this. And then I check how well actually the eigenvector that belongs to this eigenvalue is approximated by our projection. So how big is the, how well can this be approximated by a function in the subspace that we chose? So how big is the projection error? And then the theorem says actually that the approximating transfer operator t hat will also inherit an eigenvalue, this eigenvalue, up to this error. And you see this error will be small if the projection error delta is very small. So this means we know what we want to do. If we want to inherit a certain eigenvalue to the approximating transfer operator, we have to choose our subspace for the projection such that this projection error is small. So the eigenvector has to be well approximated, at least so far in theory. So I want to give you some examples that fit actually into this framework. First example is averaging. So what could we do? Here again we have our original transfer operator as an operator on this L2RD. Here you also see formulation of the transfer operator as an integral operator. So you have this stochastic kernel here. And then let's assume we decompose our variable z into two coordinates where this x is just from a smaller dimension. And what we then do is we simply average our transfer operator over the y coordinate. So we simply average out the y coordinate. And this can be seen as actually as an orthogonal projection onto all functions which do not depend actually on this y coordinate. So what you see here is the projection is defined in such a way it simply averages over y. It's also again it's in projection with respect to this mu. So you weight with this invariant measure mu. And in the end, the function qv actually does not depend on the second variable anymore. So it's simply a function which only depends on x. It's constant in the y direction. And for example, y bar is still, you could also take it away. Then you have a function really in L2RS. This is just lifted up again as a function that qv also depends on x and the y coordinate, but the y coordinate actually doesn't matter. It does not depend on it. So you could also take it out. It really doesn't matter. I want to give you an example for the setting. I mean, in terms of some potential. So here we have a two-dimensional example. So coordinates x and y. It's a diffusion in a potential, and the potential is given in this form. So you see in x we actually have it's a double well potential with minima at -1 and 1. Just a double well potential, and in the y coordinate we just have a parabola. It's just a parabola here. And then we have a term which actually couples these two things. It actually does not couple them always. You see this here. If we choose the k to be 0, then omega x does not depend on x, it's just 1. So then we just have y squared here. So then really the two variables totally decouple. In x direction we have a diffusion and a double well potential. And in y direction it's just a Ornstein-Uhlenbeck process. So it's just a diffusion in a parabola. There's nothing really going on. And if you look for this for this example here, at the dominant eigenvalue, you see this is the dominant eigenvalue, which is pretty close to 1. And if you look at the corresponding eigenvector, this is the case k equals 0, where everything is decoupled, you see that the eigenvector actually is constant in y direction, which totally makes sense because the metastability, so the slow process which we have here, is only happening in x direction. It's actually the process that jumps between the double well in x direction, and it does not at all matter where you are in y. So what you could do is you could average this now. You could average really out the y variable without having any error, because the projection error onto this space of functions which do not depend on or which are constant in this y direction is very, very small. And therefore you know that also the approximating transfer operator, which will only be then a process living on x, is very accurate. On the other hand, you see here we introduced a coupling, so we increased this slightly, so then x and y are not totally decoupled. And you also see this in the eigenvector, so it's not totally constant in y direction, so you have some kind of coupling, but still the projection error is very, very small, which means that if you compute the eigenvalue for the average system, you still see that it's a very, very good approximation of the 2D case. So this is one way how you can reduce the dimensionality of the problem and still keep the dynamics, the essential dynamics of the slowest processes. Okay, then I want to bridge maybe to what we discussed yesterday. I stick to the example with diffusions and potentials. Now I just take this 1D toy example where you have actually a rubbed potential with multiple wells. And let's say we want to discretize this actually in a fashion that we discussed yesterday by doing Markov state modeling. So what people typically do is they simply fully partition the state space with some box covering. In this case, for example, I know already where the wells are, so in this case I could do something clever and put every minimum, so every well in its own box more or less. And what people then do is they simply build a 9x9 transition matrix by counting these transitions between the boxes. There's one interesting thing. Yesterday we talked a lot about the Markovianity issue here, that this process which hops between the sets, so if I have a continuous trajectory here and I simply look at the index in which set I am, that this is not Markovian. Actually, for my construction, I first do not care about this. I do not ask the question if this is Markovian or not, because I simply want to compute this matrix. If the underlying process which gives me the matrix is Markovian or not, doesn't matter actually for me. I just use it as a tool to compute, to be able to set up this matrix. Because what you can do is exactly this matrix here that you built in Markov state modeling is again a matrix representation of such a projected operator. So it fits well into this framework. Just the projection that you apply is a projection onto this particular finite dimensional state space, namely the space that is spanned by characteristic functions on the sets. So it's a space of functions which are actually constant on my partitioning. So on the partitioning sets that I chose. This is what I can influence. I can choose my partitioning, and then I have the space here of functions which are constant on these sets. And building this Markov state model here can be actually seen as a projection onto such a state space. Why is this nice? Because you can use, for example, the theorem from before now to analyze the error of this construction of the Markov state model. So if, for example, the dominant eigenvalues are well approximated. So, for example, if you do this in this particular example, again I chose a particular value of noise for the diffusion. You see here, the eigenvalues, or you often take this logarithmic transformation, which is then independent of this lag time, which is called the implied timescales of the system. But these are just transformations of the eigenvalues. The original ones of the true dynamics, and then the eigenvalues that you get from this 9x9 matrix, so which you compute from the transitions between the boxes. What you see is that they are all underestimated, which has to happen. You can, which is actually due to that you have an orthogonal projection of the operator, so you can show that this will happen. But they are all more or less under, at least something like 10% underestimated. So, of course, this is something that one probably would like to improve. But first, one can understand where this comes from. So, what you can do is, for example, for the first time scale here, I plot again the first eigenvector, the true eigenvector of my transfer operator, and then I look at the best approximation by a step function, because building the Markov state model is nothing else than projecting onto step functions. So I look how well is this approximated by a step function, and the error that I make will contribute actually to this error due to the theorem that we had before. What's interesting here is, if you now do some analysis, or you just check where actually does the error come from, you see it's mainly in this region, close to the boundaries, of course. And that's interesting, because yesterday when we talked about this non-Markovianity of the process which switches between these sets, we said, mainly this is due to the fact that, or this effect mostly happens at the boundaries of my partition. Why? Because if I cross this boundary, because I have a stochastic process, typically the process moves quickly along the boundary and you generate a lot of transitions, which more or less, if you estimate this statistically, gives you the impression that transitions happen very often, more often than they actually do, which then leads to the fact that you think that the processes are too fast because you count too many transitions. And I think it's nice because here it's more or less the same problem of non-Markovianity that you get back, but without talking about it in this way, but looking at simply the projection error of the eigenvector. Of course, one could also use this now. If you see this and you say, okay, I want to be better here. I want to make a better approximation. What you could do is you can, of course, refine your grid. More or less, if you see this picture, you can do it adaptively. You can try to refine it where your error is big. The problem then is that, of course, you get a larger and larger model in the end. It's not 9 by 9 anymore. And if you do this in a higher dimensional state space, it will quickly become very, very costly. So you don't want to do this. Of course, this is one option, but I want to show you also another option, and we have seen this yesterday. And that's actually a very surprising option for people who work with grids and do best approximations in a set-oriented way. You can erase something from your grid. So what I can do is, I think you cannot really see anymore the sets 8 and 6. They should be a lighter gray, actually. But you can imagine where they are. So I simply have a region between these sets which is blank. There's nothing. I do not define a set there. I cut out a region which I just leave undefined. So in particular, our sets do not share boundaries anymore. There are no boundary regions where you can have recrossing or something like that. But of course, what I want to do is, or in this framework, I want to define a projection, right? I want to have a subspace, a finite dimensional space where I can project on. So before I had the full partitioning, and the full partitioning immediately gave me my subspace where I can project on, which is namely spanned by the characteristic functions, so functions which are constant. Now I have a problem. If I also want to do that, I think this picture, Jinfeng draw this to this blackboard. It's we cleaned it, so I put it here again. You have you do not partition your state space completely by sets anymore. This means what I can do, of course, is for example, for set C7, I can define a function which is 1 on C7 and 0 on all the others, like before my characteristic function. But my problem is this function is then totally undefined in this white region, which does not belong to a set. And there's one trick that I want to do, or one way how I can define in a very nice way my function, my Ansatz function in this undefined space, namely to be the so-called committer function that we have seen yesterday already. So this means, for example, for the set C7, I define a function on the whole space by being 1 on the set C7, 0 on all the other sets. And if I'm at some point in between, I define the value of the function as a probability, namely the probability that if I start here, that I will next go to C7 instead of any of the other sets. Okay, that's just a probabilistic way of defining this function. Now the crazy thing about this is that I don't want to compute this function, of course, because we also talked about this yesterday when that it's actually not so easy to, I mean, I can never compute it for every x, of course, maybe just for some of them, but also I need to do a lot of simulation to get estimates for this probability. I don't want to do that. So the question is, what happens if but I mean, I can define them, right? I can write it down in this way. But what happens now if I say I take this transfer operator object, which is kind of mysterious, I mean, I don't really know how this looks like, and now I say I just span a subspace by these crazy committers and I project onto it without knowing how the committers look like. This sounds crazy, but you can actually do this. And the very nice thing about this is it turns out that if you do that, so you project your transfer operator onto this committer space, which you do not compute, but you know it exists, and you project it onto this space, then you can compute a matrix representation as before of this operator just from just from these milestoning processes. So by counting transitions actually in this milestoning way that we discussed yesterday. So if you have a trajectory, you just, which goes this way, for example, it just stays assigned to the set more or less in the state green, as long as it, until it hits the yellow set. Then it turns into the state yellow, until it hits the next set, then it turns to the state red. And if you have such an assignment, from such an assignment of trajectories, you can immediately calculate the entries of, there are two matrices in this case, T bar and M, and get a matrix representation of this projection without having to compute the committers explicitly. So you define your committers implicitly by defining the sets. Then you know they are well defined in between, but you don't compute them there. You directly compute a matrix representation of the projection. And that's very nice that you can do this, because otherwise this would be very inefficient. But in this case, this is a nice way to really do this projection. And there's another thing which is even nicer about this. You can prove that it's better than the full partition, which means the following thing. I mean, how we constructed this, I started off with a full partition. I took these 9 sets, and then I cut out some region and said, okay, the rest is core set. So this is exactly the setup that I did here. So imagine you have a full partition. For example, imagine our 9 sets that we had before, covering the whole state space, and you have a projection which is associated with it to the step functions. And now you cut out a region, some region. This region is actually called C here. This is because it's cut out. You cut out the region C, and you get, of course, committer functions where you can also project on. Now the question is, which one is better? The projection to this to the associated committer functions, where you cut out a region, or the full partition? And what you can show is that actually, the error for the committer functions is the error that you had before, minus actually the whole error that you made in this region that you cut out. So you erase from your error, from your total error, everything in the region that you cut out. I mean, that's really nice. You erase it completely. But you have to pay for it. So this is the additional term that comes into play. And this is a ratio between two things. This eta here is nothing else than the time scale, this implied time scale that belongs to your eigenvector that you want to project. This means if you, for example, take the slowest process in your system, for example, in our example, this was like, eta was something like 17, I think. So you take a very slow process, then eta is quite large, of course. And this time scale you compare to the expected time that you need to leave the region that you cut out. The maximum time that you actually expect to leave. Maybe you remember yesterday also in Eric's and Jim Fang's talk, there was a definition of a metastability in terms of a metastability quotient. We had a similar thing there. It was also comparing the time that you need to leave or to actually to go into the metastable sets, comparing this to a timescale jumping between the sets. And this is very similar, because if your core sets that you have in the end are metastable, in the sense this ratio is actually very small, because this is, that's immediately related to this metastability quotient that we had. The row, you leave the region quickly, you enter, always if you start somewhere, you will always go quickly to one of the core sets, compared to the timescale that you're interested in. So for example, in our case, this is, if we erase, it's really sad that you cannot at all see the gray shading here. Of course, here in between there are the additional sets. The region that I cut out in between is around the maxima of my potential. If I start there, I immediately go to one of the other sets. This is no problem. In particular, compared to the timescale 17, which actually relates to jumping between these outer wells, which is my slowest process. So of course, this process is much, much slower than leaving this region in between. So this means that by cutting out, I can really erase the error. You see it also here in between. This interpolation is really good. I can really erase the error here, which immediately reflects in a better approximation of the associated timescale. So now one could be also very happy. I am totally happy at this point that one can do this. But of course one could think of, okay, what if we have really a multi-scale process like this already here? So we actually also have different scales. We have really slow process, one which is a bit faster and than others. And I want to approximate all of them quite well. What does this mean? This means that we actually have to find sets such that all these eigenvectors are well approximated by my committer functions that I have here. So with my committer functions, I have to be able to approximate each of these eigenvectors. And there's one problem if we really have a multiscale process, because for a multiscale process where you have eigenvectors which belong to, which differ in magnitude a lot, you have also eigenvectors which differ in, have a very different variation. You see here, this was the first eigenvector that we have always seen, and then you have the next one, and so on, other eigenvectors. And what you see is, the variation is very, very different of these eigenvectors. For sure, you see here you actually only have a constancy more or less on the outer two wells, and in between it's very smooth. There's no constancy at all. But for example here, you at least have around the maxima, you have a little bit of constancy where you could, for example, add additional core sets. So it's kind of a problem, because typically if you want to approximate this eigenvector well, what you have to do is you have to put more sets, of course. For example, I would have to put sets where this eigenvector is maximal to, that I'm able to track actually this variation. But this is very bad for this eigenvector on the other hand. Why? Because every set that I put introduces constancy on the set. And this eigenvector is not constant in the region in between. So for this eigenvector, it would be optimal actually if I just take two sets here and there and nothing in between. So I really I cut out a larger region, namely everything in between. So do I have to find kind of a in-between compromise? No, you can do something else, and this is also motivated by a similar motivation you have actually in PDE numerics if you do multigrid techniques. Because what you there do is you say, okay, if I also want to mimic somehow this behavior of eigenvectors, and what you can do is you can set up a hierarchical basis. So you take several grids and define which get finer and finer, and then you have take different bases associated to these grids. On the coarse level, you have actually basis functions which are also have more global support and are slowly varying. And on the finer grid, the finer grid is actually there to also be able to approximate functions like this well. And then you combine them to some basis. And the same thing you can do here actually. So what I do now is, and Now you see, that's terrible. You don't see any of my sets. They are actually not very light, but not very bright. But okay, I have to show you or tell you. I mean, here I take just two sets, two outer sets, which are actually as before. They just have the two outer wells. Here on level 2, I just add two sets to the grid. So I keep the two outer sets here and there. I just add two sets, and here I added, also in addition all the other sets such that I really have the 9 sets that you have seen before. So also here every well is resolved. What I can then do is I say, okay, I take from this grid, I take the 2 committers belonging to these outer sets. Then on this level I get 2 new committers. With respect, I take them with respect to the 4 sets, but I just look at the committers with, belong to these 2. So that I hit this set before all the other 3, or this set before the other 3. And here I have actually all 9 sets. Yes?
So when you add these 2 sets, the committer function associated with the original 2 sets also change. So do you also change them? Or?
No, actually not. It's true. If I have here 4 sets, then I would have also 4 committers, which of course the subspace is different. It does not include actually the subspace of these of these 2. But I don't do that. I just take these 2 committers and I add the 2 committers with respect to these that I get from this picture.
Just trying to
be
clear what I do.
I have it also on the next slide there. You see it actually exactly for these 2 levels. This is the case actually if you have just 4 sets. Here the 2 green ones and the outer ones. And you see all of them have a similar variation. They are 1 on the set, 0 on the others. And they have a very small support actually. This picture looks also very much to like, they are smoothened head functions or something like that. They're just 1 on whole sets, not only at a grid point. And on the other hand, if I do it the other way, I have these, on the first grid, I have my committers which are slowly varying. And from the second level, I get 2 new functions which actually are, for this, to resolve this variation in between. So which are strongly varying. And of course I can say, okay, I construct in this way a basis also consisting out of 9 committer functions, and I just project onto this space. And if you do this, here it's a small comparison chart. If you do this in the multi-grid fashion, you see that you improve actually your core set model again along every time scale. So all time scales are really improved, but in particular the slowest one, because the slowest one profits most from this nice approximation that it's really smooth in this transition region, that you do not introduce any constancy there. And of course, there is a big advantage, of both core set-based approaches actually to the full partition. Yes? Yeah? 2 minutes. Yeah, that's okay.
So what are the dash curves? They are not committer functions because they're negative.
That's true. They are the committer functions, but they are a bit shifted to be even orthogonal to these curves. But they are.
Orthogonalization with the original.
Yes. But you don't have to do that.
So the example is very nice. There's one thing that is a bit misleading here, which it would be even nicer to have example in at least 2D, because the monotonicity here introduces a bit of an artifact, which is that the sets that you take could be points, and
sure,
you cannot go, if
yes.
3 sets, there's always one in between that you need to. Whereas at least in 2D or even in higher dimension, these
totally true. Then yes, exactly, because with a pointed set you could avoid this problem introducing a lot of constancy, but you have this problem in higher dimensions, or even 2, even in 2. Yes, true. Yeah. But just to illustrate this by pictures.
You don't have. So you gain something in one dimension, which is that you can take sets that are points, but you lose something, which is that you automatically the process is monotonic. So you can't avoid. Right?
Sure. So then maybe one last thing, which is namely the benefit before was that I project onto this space, that I don't have to compute, of course, these committer functions. I can evaluate or I can compute a matrix representation of my projected operator immediately, just from a transition behavior. Now, you could think this is more complicated, of course, if I take this basis. That's even, I mean, I have the multiple levels I project onto these crazy functions. How could this work? It works in the same way, actually. You can, again, take, now these committers of these different levels, you project your operator on it, and you, again, can compute a matrix representation, but now you don't look at one milestoning process, but for each level you have a different one. Maybe, for example, if I have on level 1, I only have these two sets, this one is not there, then you see the process does not care about the set, it doesn't see it on level 1. So the level 1 milestoning process just takes these two into account. And the other one, of course, this one sees the level 2, so it changes the color here already. And from these, if you have trajectories, you have to look at the milestoning processes associated to these different levels and compute correlations between them. For example, answer questions, if this guy is green at some point in time, which color does this one get next? Does it switch to yellow or rather green? And questions like this. And from these kind of correlations, so also probabilistic things that you can estimate, you can actually get a matrix representation also for this multi-level model. And then, I think the directed network was very optional. I'm happy to tell you more about the part that I will skip now, maybe later. So thank you.
Thank you. Questions for Marco?
If you do the full projection, so this is the most simple-minded thing. That must be in some way, the quality of that must be dependent on the time step that is associated with your transfer operator.
Sure, yes.
So, then the smaller the time step, I guess, the finer this gridding has to be.
Yes.
Is there some similar sensitivity occurring for this more advanced methods? It is less pronounced. So, for example, a typical picture, if you do this Markov state modeling, if you plot the eigenvectors, typically they should have like you know that there is some exponential rule. So if you look at the exact eigenvalues and for different lag time, then they are exponential functions, the eigenvalue. If you look at this for the Markov state model, typically this works. You have this exponential decay after a certain threshold of the lag time, but before you have some other behavior. And this would be exactly a region where you would have to refine or something like this, or your lag time is just not too large. For this core set approach, you see that it's actually also for much smaller lag time still precise, so you don't have to refine so quickly, or you can also choose much smaller time steps. Yeah.
Any other questions?
Maybe.
Yeah.
So, there is a connection, as you were saying, with this metastability index, right? So here, everything relies on the fact that you know the core sets. So if I was to do, is there a way to do optimization? Like if I were to take more core sets, and then among these, I would like to find a subset, which are the real one. Can I use the error estimate that you have, in particular this eta and rho, this is like, the time it takes to get in and get out? Can I estimate that from the data and use that to do optimization?
Maybe I wouldn't call it optimization, but at least to have. I think you could also do optimization, but you can do something very heuristic first, which is also very efficient. Actually, this quotient in this case is just about. I have to think. I think it's the nominator in your metastability quotient, but actually is only about the transition region. It's not about the particular clustering of the core sets. It's just about the region which does not belong to metastable sets has to be left quickly. Yeah. This is actually for this value, it's unimportant how the core sets are joined or clustered. So what we typically do is we first try to identify, we first make the nominator small by just identifying a transition region. So we don't know where core sets are, we just want to try to find out where no core set is. So we try to cut out more or less first a region, and then cluster the rest in order to make transitions between the rest large.
problem for this is that you may create like artificial eigenvalues that you think is low-lying eigenvalues if you choose too many corsets, for example. I mean, if you, let's say, we do it in the numerical analysis where we just put in very fine grid, and the Markov state model produce a lot of eigenvalues, and you don't know what the physically really low-lying eigenvalues.
Yeah, you don't. In the approach where you want to find the corsets, you don't do a full partition first. You simply try to find more or less in the continuous space the region which you will take out. By this argument, using more or less this quotient which says, okay, you definitely need to leave this faster than a certain time scale that you set. Where you say this is my threshold, and I need to find a region which is typically always left to the other sets faster than this. And then you remain with some other part of state space which you have to split into different corsets. Then actually for the remaining state space, that's a full partition problem that you have to solve.
Okay, thank you, Marcus.